Welcome to massive open online course on basic principles and calculations in chemical engineering. So, we are discussing about the energy balances on non-reactive processes under module 7. Now, in this lecture of this module, we will discuss about again that energy balance with some examples where multiple streams will be involving without reactions. In the previous slides, we have described that enthalpy balances on non-reactive processes and also how enthalpy can be calculated based on the phase change. So, here again we will discuss with that enthalpy balances or heat balances there with non-reactive systems where there will be more than one streams will be there in the process, like evaporation process, drying process, distillation process, even and refrigeration process. How this heat energy can be calculated during the process. Now, before going to that calculation based on that principle of energy and conservation equation, we should know that what is that energy conservation equation. We have already described all those equations and derivation in our previous lectures. So, still we are actually let us having this overlook of that equation here. Here this general energy balance for an open process systems can be expressed by this equation, where delta U is the internal energy change, delta K E is the kinetic energy change, delta P E is the potential energy change, and delta P V is the flow work that is performed on the system in order to push the fluid in or out of the system, and Q dot the rate of heat energy that is into the system, and W S dot this is the rate of work done by the system as a output. So, this energy balance is to be used for the calculation of different processes where multiple streams are involving there. So, as we know that the summation of this internal energy change and also flow work performed on the system that will give you that enthalpy change of the system there. So, if there is no shaft work, no kinetic and potential energy will be there, then we can say that cancelling all those shaft work, that is kinetic energy, potential energy, we can have this simplified form of this energy balance equation as Q dot will be equal to delta H dot. Here remember that this delta H dot is basically the rate of enthalpy change for that particular systems. Now, if there are more than one streams they are in the process, then you have to calculate what will be the enthalpy for all components in the output streams, and also what should be the enthalpy in enthalpy of that components in the inlet stream. And from those that total enthalpy of those components in the inlet and output streams, we can calculate that enthalpy change there by this equation. Now, in this case remember that for the closed system this equation to be used, where rate of the energy is not being considered, whereas open system you will see that this the same equation, but in terms of rate at a continuous process we can say that this equation will be considered. And in terms of internal energy for multiple streams based processes, you will see that for closed system that internal energy change will be again that summation of internal energy of all components in the final and initial states, and from which you can get that total that internal energy change there. And similarly for open system, that we can have this that enthalpy change of this from the inlet and outlet streams. So, here it will be there may be that a final or initial here that you will see you have to subtract this. So, here instead of plus it will be negative, here it will be negative there. Whereas, for all that if there are that multiple inlets there, then you have to sum it up in inlet there all that components for each streams there. So, in this way you have to calculate this enthalpy for particular component. What should be that specific enthalpy there? That specific enthalpy will be calculated based on that what will be the enthalpy change of formation of that components, and also if there is a change of temperature from reference to other temperature, then you have to calculate the sensible heat, and also if there is a enthalpy change due to the phase change, then you have to adding up all those that enthalpy change due to that change of phases. So, in that case the summation of all these enthalpy change due to formation, enthalpy change due to the sensible heat change, and also enthalpy change due to the phase transition, then you have to get this enthalpy change for that individual components in the system. Now, let us do an example for refrigeration process. We know that we are using refrigerator in our daily use. Even for air condition we are using that air conditioner like this. How those things are actually working? Very basic principle I can show here, that that there are some components like here different units like liquid reservoirs, expansion valve, evaporator, coil, compressor and condenser. These are the several units are generally used for that refrigeration process. In this case you will see that in the liquid reservoir some refrigerant to be kept there. So, from that reservoir, that refrigerant like that refrigerant as R12, it is called carbon dichloride difluoride. So, there you can use that refrigerant, they are generally being used. So, liquid reservoir of that refrigerant as a liquid it will be there, and from that it is sent through the expansion valve, and whenever it is coming from that expansion valve at a certain that pressure, maybe that the pressure will be lower than that that inlet stream of this expansion valve, and you will see that this liquid will be coming out from that expansion valve as a liquid and vapor, and after that it will be coming through the evaporator where this liquid will be evaporated, and in that case by this evaporator heat from the certain article that is stored in refrigerator area, that will be coming into that evaporator, and after that the vapor of that refrigerator will be passing through that compressor, where the pressure will be again increased from increased by this compressor. They are at higher temperature of this vapor, and then it will go through the condenser where heat loss will be there, and this heat loss will be going to that outside there. So, that heat will be going to that outside by this condenser, and then that vapor that refrigerant again it will become that liquid refrigerant, and then it will be stored in the liquid reservoir. Again from that liquid reservoir it will go through that expansion valve and then evaporator and then compressor and then condenser, and it will be that continuously cycle will be going on. So, in this operation you will see that whenever liquid is coming from the liquid reservoir and passing through that expansion valve, the pressure will be reduced and temperature will be reduced to a certain temperature, and then it will go through that evaporator where heat will be sucked from that substances or material which is kept in that refrigerator, and by that heat you will see that it will be evaporated and then it will go to the compressor, and by this compressor there again that pressure will be increased by increasing the temperature also there. So, and it will go through that condenser to condensate that refrigerator by releasing that heat to the atmosphere. So, in this way this refrigerator generally works. So, based on this principle, and in the slides that if we use this refrigerant and flows at a circulation rate of 18.14 kg per minute, in that case you will see that for saturated fluid at a T that 258.15 Kelvin, this enthalpy change it will be for that liquid it will be 22.33, and enthalpy of the vapor for that superheated fluid it will be 180.96 kilojoule, whereas at 303.15 K that is Kelvin, this enthalpy of the liquid it will be 64.66 kilojoule, and then enthalpy of this vapor it will be 199.57 kilojoule. And for superheated fluid at temperature 318.71 K, this pressure is that is 643.28 kilopascal. There the enthalpy of that vapor it will be 209.34 kilojoule. So, here in this slide, in this schematic diagram of this refrigeration process, you will see that there are several that operating conditions or several conditions like temperature and pressure are given in the inlet and outlet of this several equipments which are being used there. So, if we consider that expansion valve, they are at inlet condition of this expansion valve, it will be liquid flowing at that circulation rate, and their pressure is 643.28 kilopascal, that is in gas pressure, where temperature is 303.15 Kelvin. And after this expansion valve, the mixture of liquid and vapor will be there at a pressure of 81.36 kilopascal and temperature of 258.15 K, 258.15 K. Here this is basically less than 0 degrees Celsius, we can say. So, here this it will be vapor form here this this refrigerant, and then it will go through that evaporator coil where that heat will be supplied to that evaporator, and this liquid and vapor will be superheated and at a temperature at a pressure of 81.36 kilopascal and temperature at 258.15 K, and it goes through that compressor where compressor outlet will have the component of vapor of that refrigerant and pressure of 643.28 kilopascal, but temperature will be higher than this that inlet temperature, that is 318.71 Kelvin. And after that it will go to the condenser where inlet condition of that condenser it will be that vapor, and also outlet condition it will be liquid of that pressure and temperature is shown here in the slides. So, in this condenser some heat will be lost, that is to the that atmosphere, and based on which you have to calculate that fraction of refrigerant that evaporates there, and heat transfer rate to the refrigerant that evaporates there. So, in this case what should be the heat transfer rate in this evaporator coil, and also you have to calculate that fraction of the refrigerant that evaporates, you have to calculate there. Now, in this case let us solve this problem. First here basis is that what is the circulation rate of refrigerant here, in this case it is basically R 12 as a refrigerant, this is R 12 as refrigerant. So, circulation rate is 18.14 kg per minute, and if we consider first that expansion valve, we can say that inlet is liquid flow rate is 18.15 kg, that is liquid refrigerant, R means refrigerant here, and here pressure is 643.28 kilopascal and temperature is 303.15 K, and at the outlet condition that the same circulation rate is there, since it will be 18.14 kg per minute, but fraction of that refrigerant will be converting into vapor. So, that will be regarded as XV, and 1 minus XV that will remain as a liquid. Then this XV you have to calculate here, that is fraction of the refrigerant which will be evaporates, and in this case the heat of vaporization is given that 180.96 kilojoule, whereas heat of enthalpy of that liquid is given as it is 22.33 kilojoule per kg. Now, if we do the energy balance over this expansion valve, we can say that here potential energy will be equals to 0, shaft work will be equals to 0, heat supply to this system that will be equals to 0, and then we can have only that kinetic energy change there. So, that will be equal to enthalpy change there, but this enthalpy change will be because of that what is the enthalpy in the outlet stream of this expansion valve, and the total enthalpy in the inlet streams there. Now, according to this we can say that if we do this material balance of this inlet and outlet streams, we can say that at the outlet streams what are the components are there. So, it will be 18.14 into XV, this is basically a vapor of that refrigerant, and this is XV vapor and into 180.96 kilojoule, since this specific heat specific enthalpy of that vapor is 180.96. So, we can say that this amount of enthalpy is there for this vapor, and similarly for other components, for that liquid component here, that is 1 minus XV, this is XV small xv. So, 18.14 into 1 minus XV into Kg, this amount of liquid will be there of that refrigerant, and here enthalpy for that liquid is 22.33 kilojoules. So, you have to multiply it. So, ultimately this amount will give you that enthalpy of that liquid in that outlet streams. Now, summation of these two enthalpy will give you that total enthalpy in that outlet streams. Basically from this equation this component will come as here, okay, summation of this two. Now, similarly we can say that other components in the inlet stream, since here only one stream is here. So, we can have this liquid refrigerant, what is this enthalpy, it is given 64.66 and amount is 18.14 kg of that liquid refrigerant. So, we have to multiply this 18.14 by 64.11 64.66 kilojoule per kg. Then you can have this summation of this component here. We can represent these things here. So, according to this equation we can write this equation here. So, from this if you solve this problem for x b, you can get this x b will be equal to 0.267, that is 26.7% evaporates there. So, 26.7% of liquid refrigerant will be evaporates in this refrigeration process. Now, next question is that what will be the heat transfer rate to the refrigerant that evaporates. Now, if we do that, again evaporator coil energy balance there, we can say that in the inlet streams the flow rate of that refrigerant is 18.14 kg per minute, and the fraction of vapor in the coil, it will be basically what is coming out from the expansion valve. It is basically 0.267 vapor refrigerant, and this vapor refrigerant will go to this evaporator coil, and you will see that it will be again going out from this evaporation coil after getting heat. That heat is not known to you. So, that heat will be supplied here. So, that heat rate to be calculated, but you will see that enthalpy of that vapor which is coming out from that evaporator is 180.96 kilojoule per kg, and at a pressure of 81.358 kilo Pascal and temperature of 258.15 K. Whereas at the inlet condition, this enthalpy of this vapor is 180.96 kilojoule per kg, whereas liquid enthalpy is 22.33 kilojoule per kg. So, here this fraction of that vapor will be coming to that evaporation coil, as well as other part of that refrigerant, that will be 1 minus 0.267, that fraction of refrigerant as a liquid, it will go to that evaporator coil. Now, in that case we can say that here what will be the amount of energy that is supplied. So, accordingly again if you do that energy balance, so we can get that potential energy, even shaft work, that will be neglected. So, we can have this that q dot will be equal to delta H dot. Now, q dot, from this we can then have that from the enthalpy change. So, what is the enthalpy in that inlet condition of this evaporator coil? This will be there. Again what will be the vapor component, this is here simply this, whereas the outlet streams, that vapor this is your outlet conditions, whereas inlet conditions, this this will be your liquid that refrigerant. So, we can say that here this is basically this liquid components is 0.733, this is 1 minus 0.267 we can say. So, this fractions of liquid will be entering to that evaporator coil, which will be evaporated, along with that vapor which is coming out from that expansion valve. So, that also will be there. So, adding up all those enthalpy change, and after balancing that, finally you can have this value of q dot will be equal to 2110.11 kilojoule per minute. So, in this way we can calculate what will be the heat energy to be supplied to the evaporator coil to evaporate that liquid refrigerant, and it will be passing through that compressor at a certain pressure there, that will be calculated in this way. Let us do another example of distillation process, where you will see that several output from that distillation column will be there, whereas one inlet of that feed streams will be there to the distillation column. There as an example here, like let it be acetone and acetic acid mixture. It will be passed through that distillation column, where it will be evaporated based on that boiling point temperature. And in this case from the bottom of that distillation, the product will be coming as bottom products of certain percentage of acetone and acetic acid, and it will be recycle to that distillation column certain amount, that will be as boil up. Whereas from the top portions that evaporates, or you can say vapor phase, it will be coming out from the top, and then through the condenser it will be sent, and so that after condensing that vapor components, it will be coming liquid, and some amount of that liquid will be sent back to the distillation column as a reflux, whereas other portions will be taken out as a overhead product, like some percentage of acetone and acetic acid. So, in the overhead product, since the acetone has lower boiling point than acetic acid, so we can say that maximum portion of acetic acid will be in the overhead product, whereas that a small amount of acetone will be there in the bottom product, whereas maximum portion will be acetic acid as a liquid in the bottom part of the distillation. And from this bottom part, one reboiler to be used to send back to the distillation column certain amount of that product for again distillation process. So, in this way it will be that continuously operated this distillation column, and in this case you have to calculate that what will be the net heat required for the process, and also heat input to the reboiler and heat removed from the condenser, that you have to calculate. Based on that certain amount of feed, like here 100 mole of feed as basis, if you consider, then what should be the net heat required for the process, that you have to calculate. So, for this you need some data. So, from the steam table you can have this data of like this. For feed, if we represent it as 1, and for that feed liquid at 67.5 degrees Celsius of the mixture of 65 mole percent of acetone and 35% of acetic acid there, and in the overhead as a stream 2 we can have this that vapor of 63.0 degrees Celsius, where 98 mole percent of acetone and 2% of acetic acid will be there, and in stream 3 you will see some amount of liquid overhead product will be sent back to the distillation column there, and there you will see that it will be sent as a reflux. So, we can have this reflux, and that will be as a liquid, and it will be sent to the distillation column at temperature 56.8 degrees Celsius, whereas the composition will be the same as that it is coming from the overhead product there. Similarly, you can say that the overhead product from that stream 4, that will have the same composition and temperature there, what is sent back to the distillation column as a reflux. And bottom product, we can say that in the stream 5 here temperature will be 98.7 degrees Celsius, and mole fraction of that components will be 15.5% of acetone and 84.5% of acetic acid, and you can say that after reboiling of those liquid components by that reboiler as a boil up to be sent to the distillation column at a temperature of 98.7 degrees Celsius, whereas mole fraction of that acetic or acetone, it will be 54.4 mole percent, and acetic acid will be 45.6% of that. So, in this case you have to find out at a different temperature of these different streams what will be the thermodynamic data like this here, what will be the enthalpy change there, that you can get from its steam table. Here it is given in this table here. So, from this we can of course calculate that different we can say that we can do that energy balance to find out that net heat requirement for the process. Now, we can actually outline this whole schematic diagram with the different temperature and mole fractions, all those things here in this picture as shown in the slide. So, please go through this, what will be that fraction of that components it is coming out from the top of this distillation column as overhead, and what will be the fractions of that components that is going into that distillation column and it is coming out bottom products there. What will be the QR that is heat is required for the reboiler, and also what is the temperature. So, all these actually mentions here in this this distillation column. Now, if we do the balance, now this balance maybe first of all you have to do that material balance, how much that overhead product is coming, how much bottom products is coming, also to be calculated based on the material balance. Here material balance and energy balance simultaneously will be considered. So, at a that certain rate of that feed will be distillate, and it will be coming out from the overhead product, and it will be coming out as a bottom product. Now, what will be that amount that is not known to. If we do the material balance, we can find it out there. Now, if we do that overall balance as a total mole there, so we can say that here inlet is 100, that is 100, and what will be the outlet, that that outlet is here is given as per this diagram. It will be that 0.5 into as mentioned in the diagram, and your plus here N5 is here. What is that? This is your N5, that is bottom product. So, in this case we can do this overall material balance here by this equation, and then if we do the material balance for acetone here, in this case we can say that 0.65 into 100, then it will be equal to 0.98 into 0.5 N2 plus 0.155 N5 according to this this material balance there. So, acetone, for acetone, if you do this component material balance and solving these two equation, we can get this N2 will be equal to what, 120 mole, and N5 will be equal to 40 mole. What does it mean? That the moles of total moles coming out from that distillation column as a vapor, it will be 120, whereas as a bottom product, this amount is coming out as N5, it is 40 mole. So, we can say this here that product flow rates at the overhead stream here. So, it will be as 0.5 into 120 into 0.98. So, this will be equal to simply 58.8 mole A, and B will be equal to 0.5 into 120 into 0.02, it will be 1.2 mole B. And at the bottom what will be that amount of mole A and mole B here. Here mole A means here you will see that here basically that acetone, and mole B is basically that acetic acid. So, we can say here this amount of acetone and this amount of acetic acid will be coming out from the bottom. Now, if we do the overall energy balance here, in this case again that potential energy is to be neglected, and shaft work to be neglected, and also that delta ES some that other phase change energy will be negligible. So, overall we can say that this is kinetic energy, you can say that will be also neglected. So, overall we can say that this Q will be equal to delta H, then here it will be summation of Ni H I minus Ni H I there. In this case what will be the inlet and outlet streams, based on which we can do that energy balance here. Now, from this energy balance we can then write directly that Q will be equal to here, and after substitution of this value in this inlet and outlet conditions, then we can have finally this value of 2.16 to 10 to the power 4 calorie. Now, in this case incorporate the value in the table whatever it is given at a different temperature, that these values are there. And after that you have to find out what will be the heat loss in the condenser, that also calculate by material balance, what will be the amount of that moles of acetone in flowing through that condenser, and also what will be the moles of that acetic acid is flowing through the condenser. So, accordingly you can do again that energy balance for that condenser. Now, accordingly if you substitute that value of enthalpy there, you can get this enthalpy change as here 8.77 into 10 to the power 4 calorie, that will be heat removed from the condenser. Now, in this case assuming negligible heat transfer between system and the surroundings other than QC and QR. So, we can have this QR will be equal to Q minus QC, that will be equal to here we can say 2.63 into 10 to the power 4 minus 8.77 into 10 to the power 5 here, from which we can say that this 9.03 into 10 to the power 5 calorie heat to be added to the reboiler, because this QR is the that reboiler heat energy supplied to that reboiler, and Q is the here total energy that already we have calculated by this equation here, total heat required for the process. And if you subtract that condenser heat what is coming out from that condenser, then you can get this what will be the heat is actually supplied to the reboiler there. So, in this way you can do the energy balance for the distillation column. Now, let us do another example of evaporation process based on this energy balance equation. So, in this case if we consider that a solution that contains 5 kg salt per 100 kg solution is evaporated to 20% in an evaporator. The heat capacity of the solution is 0.98 kilocalorie per kg degree Celsius, and that of 20% solution is 0.90. Now, the feed temperature is that 30 degree Celsius, whereas boiling point in the evaporator is 105 degree Celsius. It requires 540 kilocalorie to evaporate 1 kg of water from the boiling solution. Now, the steam gives up only its latent heat of vaporization as 525 kilocalorie per kg. Now, based on this principle, you have to calculate how many kg of steam is required per kg of feed, and also it is proposed to run the concentrated solution through a counter current heat exchanger to preheat the feed. If the concentrated solution you can say is thus cooled from 105 to 50 degrees Celsius, in that case how much heat is to be transferred to the feed stream, there you have to calculate, and what percentage decrease in the steam consumption will result as per this problem. So, let us do this calculation here for this evaporation process. As a basis, we can take 100 kg of solution where 5% in weight percent you can say salt will be there subjective to that evaporation. And in this case as per figure here this is one evaporator as shown here in the slide. F is representing here as that feed solution of 5% salt which will be entering to that evaporator, which is to be evaporated, and P is the product solution of 20% of salt, and E is the evaporation amount, that is in kg. S is steam that is used for that evaporation, and C is the condensate that is obtained from the steam zest in kg. Now, if we do the material balance to find out all those stream amount which is coming in and coming out, based on which we can get that E will be equal to here 75 kg and P that is product solution of 20% salt will be coming as 25. So, in this case we have to do the overall balance like this, F will be equal to E plus P overall balance here for the solution, and salt balance, if you do that in the feed stream the salt amount is 5%, whereas product stream salt amount is only 20%. So, according to that salt balance we can simply calculate this what would be the product that will be coming out from that evaporation. That amount is equal to 25 in kg, and hence if you substitute this product value in this overall balance, you can get what should be the evaporation amount there as E, and that is 75 kg according to this calculation. Now, you have to do the energy balance there. Now, for that energy balance you have to consider some reference temperature. In this case we are considering that reference temperature is 0 degree Celsius. Now, we have to first calculate what are the heat input there. Now, heat with feed, that will be equal to, since feed amount is 100 kg and that specific heat of that feed stream is 0.98 and temperature difference is that 30 degrees Celsius. So, we can say that this amount of that is 2940 kilocalorie of heat will be with the feed. Similarly, heat with the steam that is entering to that evaporator as here S into H plus 525 kilocalorie, where in this case H is sensible heat we are considering, S is the that amount of steam. So, we can simply that calculate the S into H, this is enthalpy for that is sensible heat change for that S amount of steam there, and that also there will be a certain amount of that latent heat that will be equal to S into 525 there also. So, this amount of heat will be supplied to that evaporator, and heat output that will be come out heat with vapor, and it will be simply that E into Cp dt plus lambda. Again this lambda is the latent heat of vaporization. So, here after substitution of that Cp value and temperature difference is 105 and E amount is 75 and that latent heat of vaporization is 540 kilocalorie, then we can have this that 48217.5 kilocalorie there that is heat with vapor. Similarly, heat with product, that will be equal to 25 into 0.9 into 105. This is the amount supplied, that is the amount is coming out as a product, and 0.9 is that specific heat capacity and 105 is the temperature difference, and based on which we can say that this is simply that sensible heat of that product. So, it is coming out as a 2362.5 kilocalorie. Similarly, what should be the heat with condensate, that also to be calculated. Here condensate here in this case only simply that is to convert that vapor into condensing form. So, for that you need some heat of condensation, that will be equal to H here. So, S dot H will be the total amount of heat with condensate there. So, assuming heat losses to be negligible here, all the heat will be utilized there. So, in this case heat input will be equal to heat output there. So, here we can say as per that balance of that heat we can write simply this equation, and from which after substitution of this sensible heat and also you can say that other components there, and then you can get what should be the amount of steam is supplied to that evaporator there. So, it is coming out as 90.74 kg, that is supplied as a steam to that evaporator to evaporate those solution there inside the evaporator. Hence, kg of steam required per kg of feed, it will be simply that is 90.74 divided by feed amount, that will come around 90% there. So, in this way you can calculate what should be the fraction of feed stream as a steam that will be supplied to the evaporator to evaporate those solution there. And then again you have to calculate that what should be the heat transfer to the feed stream there, that is basically the heat lost by the product stream. So, here in this case from the material balance is same as that in the part A, you have to calculate that different stream amount based on that, and since we have done it in part A, so we have to use all those amount of streams of F, S, E, C, P, all those things here itself in this part of this problem. So, in this case heat transfer to the feed stream basically considering as Q, and that will be equal to heat lost by the product stream there. So, this Q will be equal to P into Cp into dt according to that sensible heat. Based on that specific heat capacity at constant pressure and the temperature difference. So, it will be coming as 25 into 0.9 into 105 minus 50, that is basically 1237.5 kilocalorie. Now, let us consider that what should be the temperature of that feed after heat exchanger there. So, in this case if we consider that temperature is Tf, so we can say simply that this heat balance as F into Cf. Cf is the that specific heat capacity of that feed stream, and F is the amount of feed is supplied to that evaporator, and the feed temperature is, if it is Tf, then from that steam temperature we can subtract it, then we can get that enthalpy change of that feed stream as here 1237.5. So, in this case what should be the temperature of feed stream. So, after solving this equation of this heat balance there for this feed stream, then we can say that Tf will be equals to 42.62 degrees Celsius. Now, heat content of feed, that will be is equal to 100 into 0.98 into then 42.62 degrees Celsius. This is your temperature difference from the reference temperature of 0 degrees Celsius. Then finally, you can say that heat content of the feed will be equal to coming at 4176.76 kilocalorie. Similarly, if you do the heat balance around the evaporator, then you can say that this amount of feed that is entering and according to that what will be the energy is there, and what will be the energy supplied by that steam, and that will be equal to what is that it is that is coming out from that product stream there, and also from that vapor components there from the evaporator. So, after substitution of this value, then we can solve this S will be equal to 88.38 kg. Now, in this case you will see that decrease in steam consumption, you will see that it will be coming as 90.74 minus 88.38 there, because in this case this steam is 88.38. So, earlier that steam was 90.74. So, basically the reduction in steam consumption will be equal to 2.6%. So, here in this way we can calculate that reduction, that is what percentage of decrease of steam consumption results if that we propose to run the concentrated solution through a counter current heat exchanger to preheat the feed if the concentrated solution is thus cooled from 105 to 50 degree Celsius. So, in this way we can calculate also the feasibility of that using what will be the amount of steam for that evaporator. So, before that just changing this temperature condition and also preheating condition, you will see that maximum amount of heat is required for that evaporator. So, to economize that process, what you have to do, you have to preheat the solution by a certain heat exchange equipment, so that you will that utilizing less amount of steam for that evaporation process. Now, let us do another example for solving the energy balance for that processes based on that energy balance equation. Let us do the example for drying process. Now, problem is that in a spray dryer, a liquid solution of the material to be dried is sprayed into a steam of hot gas. Now, inlet air is given at 4000 meter cube per hour, that is measured at normal temperature and pressure, and temperature is 300 degrees Celsius, and 780 millimeter mercury of pressure, and there per kg of dry air contains 0.005 kg of moisture there. Whereas inlet solution there 300 kg per hour to be supplied, where 15% solids will be there at 20 degrees Celsius. So, you have to dry this solution of this 15% solids, that is called slurry. Now, at the outlet solid, the temperature is 40 degrees Celsius, whereas outlet air you will see that condition is 90 degrees Celsius, where moisture content will be 0.035 per kg of dry air at a pressure of 760 millimeter mercury. Now, in this case you have to calculate the composition of the outlet solids and the radiation loss there. Assume that specific heat of dry solids to be 0.2 calorie per gram degree Celsius, and that of gases to be 0.24 calorie per gram degree Celsius. Let us do the solution or solve this problem here. In this case, consider that 1 hour operation of that spray dryer. Here it is schematically represented in this slide. Here the spray dryer, here inlet is solution at 20 degrees Celsius, where inlet air containing that certain moisture at 300 degrees Celsius to be supplied to that spray dryer at 300 degrees Celsius, and after drying you will see that outlet air will be coming at 90 degrees Celsius with a certain moisture content, and then solid whatever it is coming out as a dry product, you can say that it will be at 40 degrees Celsius. Now, based on this schematic diagram and their streams, you will see that you have to do some material balance to find out what will be the moles of that is air is or solution is coming to that spray dryer, all those things. Now, assume that air and the accompanying water vapor behave as ideal gas there. So, in this case let N0 number of mole of air and water vapor combined is coming to that spray dryer. So, in this case since it behaves as ideal gas, so we can write this ideal gas equation here. N0 will be equals to PV by RT. So, if you substitute that pressure and volume there, and that R value, that is universal gas constant, and then temperature of this normal temperature. So, we can say that 178.7 that is 57 kg moles of that air and water vapor mixture is coming to that spray dryer. Now, you know that in that inlet condition that water moisture per kg of dry air is 0.005 kg, whereas if you convert it to mole, then you have to divide this kg or mass by its molecular weight, and finally you can say that 0.008 that moles of that air and water vapor combined is coming to that sprayer. And kg mole of wet air by kg mole of dry air, you can get it by this here, simply just adding up that 0.008 to that 1 mole of dry air. So, this is the ratio of that kg mole of wet air by kg mole of dry air. After that what you have to do that you have to find out the what will be the amount of dry air that is entering, that amount of dry air entering to that sprayed air, that will be equal to simply that 178.57 by 1.008, that will be 177.15. And amount of dry air, then in terms of mass, it will be coming that since it is a moles, then you have to multiply it by molecular weight, then it is coming as 5109 kg. Now, amount of water that is removed by air after drying, then it will be as simply here that 5109 kg of dry air is coming. Then what is that moisture at inlet and outlet. According to that you can calculate what would be the moisture in that removed by that drying process. Now, initial solution that contains that 15% solids, water in solution, that is 255 kgs, solids in solution, that is then 300 minus 255 kg, then it will be your 45 kg, that is in solid solution. Now, water left in the final solids, this is basically 255 minus this 153.27, that is your amount of water which is removed. So, water left in the final solids, it will be equal to 101.73 kg. Now, accordingly you can calculate what will be the composition of that outlet solids. Now, solids is 45 kg, weight is 30.66%, water is 101.73 kg, then weight percent will be 69.34, total is 146.73 kg, and then weight percent will be 100% there. So, accordingly you can calculate what should be that mole fractions also there. Now, if we do the energy balance over this spray dryer with reference temperature of 0 degree Celsius, then we can have this heat with solution here 300 into 1 into 20 at the temperature here it will be equal to 6000 kilocalorie. Heat with inlet air, it will be that there as per that moisture content and its specific heat capacity, and then at that temperature difference, then it will come ultimate 369,687.24 kilocalorie. Similarly, heat output that will be calculated as per this heat with solids, this is this amount and that is simply CPdt into what is that amount of that solids there. Heat with outlet air, it will be coming as this amount. Heat utilized in the process for vaporization of water, simply this one. So, this amount of heat is basically utilized there. So, what will be the loss of that heat energy there? Now, you know that heat input is there, what will be the total heat input there we have calculated, this is 6000 plus that heat with inlet air and also heat with solution, this total amount will be as heat input. Whereas you will see that heat utilized in the process for the vaporization of water is 42915.6 kilocalorie. Now, if you subtract it, you will get that what is that heat output there. This heat output is basically that 1173.84 and plus 114,216.80. Now, if you subtract these all that heat output, heat utilized from that heat input, you will see that this amount of heat will be lost by that radiation. So, this is you know that a basic calculation for this spray dryer for energy balance and what will be the amount of heat or amount of enthalpy to be supplied to that sprayer with that solid solution, and how that solid solution can be dried after just removing of heat energy by evaporation process, or just by changing of enthalpy and also the moisture content of that dry air in the inlet and the outlet condition. So, these examples will help you to solve other different types of problems based on this concept, and also we have discussed that the problem of energy balance for the distillation. We have described described the enthalpy balance calculation and how to do this for refrigeration process, how to do this for evaporation process, and also this drying process. I would suggest you to further practice on this type of problems from these textbooks. It is given here in the slides. I think it will be more useful if you do the practice on this example given in the textbook there. So, I also here suggest to consider the problem whatever discussed in the slides today's lecture, to practice again and again, so that it will be that useful for you to further understand the solving of other other different types of problems based on this energy balance equation. In the next class we will try to discuss more about that energy balance with more example there with different inlet and outlet streams, and also we will discuss something more about that energy balance with some reaction processes there. So, thank you for your kind attention.